Last time we finished up the front end of the compiler. We looked at how lexing and parsing work and how type checking works, where we can enforce some rules of usage of symbols in our language using type annotations, and how we went over an algorithm for actually enforcing those rules in the compiler. And hopefully by now you've at least started or taken a look at the type checking project and how you can actually implement this algorithm. And today we're going to start on the back end of the compiler, where we look at how we take this tree and we use it to generate assembly code that is hopefully an equivalent program to our input simple C program. But before I get into that, let me cover a couple of things. So I think I should go over the homework, right? Everyone would like to see the homework. And then go over the project a little more, show some more examples, answer any questions you might have. So first, let's look at the homework. So this was the exercise. It was to create a parse tree, and like in class, we could do a limited parse tree for this, and then just walk through the tree, updating the symbol table and checking the program against the typing rules that we have in our project too. So any questions before I begin about this? Okay. So I'm going to make a kind of simplified tree for this. You can certainly make the entire parse tree. But the top level note here, if you look at the AST definition, is a program. That program is a list of external declarations. So we have int x, and then the main function. Inside the main function, we have a list of declarations. And statements. Oh, sorry. So here's the parse tree that has been created. At the top, we have our program. Our program has external list of declarations, so we have int x, and followed by main. And underneath main, we have two declarations, int x and int y, followed by two assignment statements, y equals 2, x equals y, and then the mandatory return at the end of main. Here's y equals 2, and x equals y, and then return is mandatory according to our grammar. Okay, so what data structure do we use to hold the types of our symbols as we do our type checking? Symbol table. Good. So our symbol table is just a mapping from the symbol name and its type. And in our implementation, we can just use the AST tree structure for types as to represent our types in our symbol table. Okay. And so I traverse this tree in a post-ordered fashion. And when I see this declaration, what happens? Well, I store it in the symbol table, right? And I give it the name, the type, int. Yeah. So let me go to the type rules to base it on our type rules. So the type rule for declaration is just to bind the declarative symbol to its type. And now when we enter main, we only have a single symbol table here, and I think I only showed you single symbol table examples. But if we look at the rules for doing type checking function definitions, the way we manage types in multiple scopes is we create a new symbol table for each scope that function is in. Now, maybe some of you figured this out for the homework, maybe some of you didn't, but let me explain this to you now. So each time we enter a new local scope, be it a function scope or a compound statement, in order to implement this C-style scoping rules where we can access the symbols from any parent scope unless we've redeclared the symbol. The way that works is when we enter a new static scope, like in main, we create a new symbol table for that scope. So this symbol table that we created was for the global scope. And when we enter a new scope like main, we create a new scope, and I've given you API calls to actually create that, and it'll create a new symbol table for you. And so what that looks like is we get a new, entirely fresh symbol table. Now there are several ways to implement this. You could use a single table to do it. The implementation I've given to you is to actually create a new symbol table for each scope in the program. So now, when we continue traversing our program and we see this declaration in X, we'll store it in the most local scope that we have available to us, which is the main scope. And same for int Y. And so now when we see an assignment statement, this is the typing rules for assignment statements. We first get the type of the left-hand side and the right-hand side of the statement because they can both be expressions in our language. And so let's do that now. And so just note that in order to be able to support pointers, like in C, you can have a dereference on the left-hand side, or you can have an array reference. The left-hand side can have three different kinds of expressions that are allowed to be assigned in our language. So in the C world, these are called L values, and L values are just basically addresses that you store to. We'll see how those actually work when we go to generate code. But from our point of view, all we really need to do is check both the left side and the right side, get what type it is, and compare those two types. So here when we see y equals 2, how can we figure out the type of the left-hand side of this assignment? Well, we just look it up in the symbol table. So if we look up y in our symbol table, then we find that it's int. So we see that the left-hand side is an integer. And then the right-hand side is just a constant in our language, an integer literal, and we just build that into our type checker. Yeah?
So let's say we didn't find y or x in that first symbol table. Would we refer to the symbol table as x?
Yeah, exactly right. And so, exactly right. So well, okay, let me go through this one, and then let's look at the x equals y in both cases where it's declared in our scope and not declared in our scope. And just to kind of preview the implementation a little bit, I've given you code to look up the type of a symbol in any scope. So this is the function that will look up the symbol, to look at the type for you in the symbol table, as long as you've constructed the symbol tables properly. So for 2, this is just built into our language. Whenever we see an int expression, a constant int expression, then we can just always return the int type. And in our, if you look in our example, or you look in the, there are built-in built-in constants for you for referring to the primitive types in our language. So you just return int type. Yeah?
I think there's also a string array type. Yes, there is. Are we supposed to use that too?
Oh, let's see. You mean in the code?
Okay.
A string array type.
Yes. Those words exactly.
Oh, array type. Oh.
Let
me see what you're talking about.
Not just an array type, a string array type specifically.
Let me take a look. string.
Because I couldn't find a way to use it while writing Gus that wouldn't require a lot of fancy, like.
Where is it defined?
Typecheck.c, line check.
Just see. String. Oh, yeah, I see it. Let me make sure.
That's assigned on line 64.
Okay, I see it. String array type. I've given you the code to use it. So it's for the argv in main. If you look at check prog and check main, which I think I've given you, it's being used there. But yeah, you won't have to use it. You won't have to use it yourself. Is it in your template? It should be in your template, right? Being used. It should be in check main, which is here. Yeah, sorry for the confusion on that. So I think I was trying to support more than what I'm requiring you to support in class. But this is where it's used. But no, you won't have to use it in your type checker.
So actually, on that topic of supporting more than is defined in class, what are we supposed to do for undefined behavior?
Oh, for undefined behavior, you mean in the type checker?
Yes. For example, if there's an array expression that has a non-integer index, that's the referencing at.
Yeah, that's a good question. So we won't test it if it's not in the type specification. But generally speaking, you can always in C, undefined behavior is handled both in the type checker and also in the compile time, and also sometimes it's not handled at all, and just allowing the machine to throw an error. So yeah, this is not going to be like a strongly typed language or statically checked in all possible bad behaviors. So basically, if you'd like to do stronger checking, by all means do it. But we will only check the specification that's here. But that's a good question. And there are lots of other undefined behaviors, like reading outside the bounds of an array that we definitely won't have to check here. Okay, so the type rules for assignment statements. Once we have found the left and right side of the assignment, then we can check that they match according to the rules of our language. And in your implementation, I've given you a function that will do that for you. So you just give it two type AST structures, and it will compare them for you and give you a true or false. So okay, so this type checks, and then when we get to the next one here, in C-like languages where we have static scoping and variable hiding, where you can redeclare variables in a nested scope, you get the type of the symbol that's in the closest scope to you, closest scope to the point at which you're using that symbol. So because X is declared locally in the same scope as this X, when we do the lookup, we look up in the local symbol table. But if we had written the program differently, where a declaration were not there, then this declaration would never have been added to the symbol table. Then we go to look up X, we first look in the local symbol table, and then if we don't find it, we pop up to the parent symbol table and keep going until we find a declaration of X. So this is just the kind of static scoping language design that I'm sure you're familiar with using in C, where you can declare local variables, but you can't declare the same variable in the same scope. This is how it's implemented. You just have this nested list of scopes, and each is associated with a symbol table. And then in order to actually implement the lookup, you just look at the closest scope, go to its parent, look at its scope. If it's not there, go to its parent until you reach the global scope. But you won't have to implement any of that. I've given you functions that will do these lookups for you. And I think I've given you examples to show you how to use these as well. Yeah, and I'll go over examples for implementation as well. Okay, so in any case, whichever version of this program we had, we'd find that the type of x is int. And similarly, when we look up y, we'd find that the type of y is also int. These match, and so this program is type safe. If, for instance, the global scope had char or some other type, like pointer, then x would not be an int type, and compare types would fail in our language. Questions on this so far? Did anybody get anything different? Yeah.
So I noticed this is a more simplified form of the ASD. So if we have our int declarations under one common node within the main scope, like the sort of near declaration list, would that be
Yeah, that's fine. Yeah, that's more accurate to what the actual ASD looks like. I'm just doing this in a simplified way. And also, there's also type checking for this return type as well. So according to the type checking rules for the main function and for functions in general, we also check the return expression for type errors. The return expression's type should match what? What should the return expression's type match? For type of the function, right, exactly. So for main, this is built in to be int, and I've given you the code for main already, so you don't have to implement it. But for main, this is what it looks like. For the function, when you actually have to implement type checking for the function, you'll pull out the return type from the function type. But once we've checked the return expression's type, once we've found its type, then we can just compare that return expression's type to whatever the function's return type is. For main, it's always int. That's just built in. That's the code I've given you. For a function, you just get that from the function's return type. So if we were to do type checking on 0, this is also built in to our language. So I can't remember if I gave you this in the template, but this is all the type checker does for int expressions. So int expressions are always int type. And so when you go to check an int expression, you can always just assign the type of that tree node to be int. So that's how the type checker knows 0 has type int. The type checker builds in the fact that main always returns an integer. And so we just compare the return type that we found from the return expression to the function's actual return type. And then, it's a type error if it doesn't match. Otherwise, it's not a type error. And so main is an example to build on for how to check function types, because it shows you how to create and destroy the scopes, which will hold the symbol table for you. It also shows how to access that symbol table and update it, and how to compare types. Okay, questions on the homework? Yeah.
Remember how you kind of defined multiplication as an operation in the symbol table?
Yeah.
Would you consider assignment to be like that? Do you give any both types you can match like this assignment?
It is effectively. It is effectively like that. When I wrote it, I didn't implement it like that because you could actually implement it like that. You could implement it as a function that that takes, two values. I think the difference is that for an assignment I think this question was actually asked on ed discussions. In C, an assignment is actually an expression in C, which is why you can say things like, so in C, let's make this bigger. In C, you can say things like x equals y equals z. And the reason you can do that is because y equals z is an expression in C. In our language, I made it a statement just to make it a little easier to compile the language. It's also a sort of a questionably useful feature. It's certainly useful to say things like this, but a common mistake that programmers make is to forget to use double equals for comparison. And so this is kind of a classic bug in C programming where, so I guess if I write this program here, let me quiz you on this program here. So if I have this program here and I run it, what will the output be? Yeah. It'll always be yes. Yeah, exactly. Good. It'll always be yes. Because deceptively, this looks like you're comparing C to 1, but you're actually assigning C to 1 here. And because it's an expression that has a value to it, the value of it is going to be 1, which is why this works. If I say A equals C equals 1, then the result of this is equivalent to saying C equals 1 and A equals C. These are the same thing. And saying C equals 1 is equivalent to assigning C to 1 and also producing the value 1. So this is equivalent to saying if 1. But in simple C, I tried to simplify this a bit and just make it a statement. And so, but it does have this same functional feel to it where it takes two parameters, the two things you're assigning. Its return type, you can think of having no return type in our language, a void return type or unit return type, depending on how you frame it. Just like all statements in C don't have any return values, you can think of them as expressions that have a void return value, a type that always is empty. It's another way to think of it. All right, good questions. Other questions on the homework? So since last time I've put up example implementations that I was meant to go over last time, but I think I just ran out of time. So let me go over the implementations for parts of the type checker. So here is the code for implementing checking declarations. So let me go over the specification first. So the specification just says bind the declared symbol to its type, and we do that by using our symbol table to store its type. And then the only type error we need to check here, or I've given you to check here, is to see if it's a redeclaration. So if it's already been declared in the symbol table, then that should trigger a type error. So here's the code for implementing those typing rules. We first look up the symbol table, look up the value, look up the name of this declaration, the identifier in the symbol table, and this is how you do the lookup. Now, the kind of subtle difference here is that we're using the lookup function, which is different from this lookup in all scopes. So lookup just looks in the current scope, none of the parent scope. So why, for our simple C language or C-like languages, why would we only check for redeclarations in the current scope? Yeah. Yeah, exactly right. Because at least in our design of the language, just like in C, you're allowed to redeclare symbols in a nested scope, even if it hides parent scope symbols. And this is really just a design decision. You could also write a language where you only allow unique symbols in the whole program. But we're implementing a C-like language, and this is how the implementation works in C. you make a distinction between looking up symbols in your current scope versus looking up symbols in all the scopes. And so I've given you both functions here, and it's exactly right. In our language, and this is just by design, just like in C, we only need to check in the current scope for redeclarations. And so this is the code for doing that. This is how we access the current symbol table. This is how we would access the identifier of the declaration. And this is how we would generate a type error. So null, and if you see the specification here, if the symbol is not found in either of these cases, the function returns null. So if it returns something other than null, we have a type error. And the type error function will automatically generate the exit code for you. So as long as you call type error in the right spot, doesn't matter what the message is, our grading scripts will only look at the exit code of the program. Otherwise, if it's not a type error, this is the code for inserting symbols into the symbol table. So we get the current table from our current scope. This is how we get the identifier from the declaration. And the symbol table just stores the AST structure for our types. So our types can be parsed by the AST. And so we just reuse that AST, the way I designed this was just to reuse that AST structure for specifying the types. Questions on that? And here, I think I showed this earlier, this is how you would create a built-in type in the language for integers or characters or whatever primitive types we have. All it does, it just sets the resulting, sets the resulting type of the expression to be one of our built-in primitive types. Questions on that one? Yeah. No, you don't. You don't have to check. And so why might that be the case? How or what guarantee do we have that int expression, if we have an int expression on the tree, what guarantee do we have that it actually is an integer? Or do we have any guarantee? Yeah.
You're checking the kind of the check expression, the check expression function. So that should have been picked up. The kind should be set by your parser.
Okay, the parser sets the kind. So how does the parser know to turn this into an int expression? Yeah, the lexer. We just looked at, I mean, this is kind of the definition of our language, but because int expression, the parser only parses int expressions if we have the ASCII number symbols, then the parser is already guaranteed for us, we guaranteed for ourselves that we only create int expressions for ASCII digits, and just by the definition of our language, if we see ASCII digits, then we just define that that's integers. So there's really no kind of inference here. It's just definitional. It's like axioms basically. So if you think of the type checker as a logical inference tool, then we just define what the axioms are. So we say if we see ASCII symbols for numbers, then we just, as an axiom, we say we're going to define that to be integer types. But yeah, that's a good question. It's a subtle point, that it's really the parser that is enforcing what number symbols look like. And because of that, we can rely on the parser and the lexer to do that. We can just define those symbols to be integer. All right, let's look at a more complex one. This is the check for identifier expressions. So this is, for instance, here, when we check, say, y is an int expression. And what we did was we looked it up in all symbol tables. We want to look it up in the local symbol table, and then if it's not there, look it up in the parent symbol table. So we want to look up the type of y if it's there, and then set the type of the AST node that holds that int expression to be the type that we found in the symbol table. So it's not doing much. It's just taking the type from the symbol table and attaching it to the tree, annotating the tree. Becomes more interesting when you actually do arithmetic expressions and you infer what the type is. But here we're just literally pulling it out of the symbol table and annotating the tree in order to figure out what the type of that tree is. All right, so here's what that code looks like. So here's the code for looking up a symbol in any parent scope. So I've given you the function already, look up in all scopes. It takes whatever your current scope is, and if you look at check main, that's managed by main and compound statement and functions. And this is the symbol of the identifier that we're looking up. If it's not defined, that is, if the resulting binding we get from the symbol table is null, that's a type error. And in the type specification, we can only use variables that are not declared as a function, that are declared as variable types. So I think this should be in the specification here for ident expression. Okay, so I didn't require you to do it, but there's code. So we won't test that, but there's code to show you how to, because you'll use this in other places. There's code. This is how you would check whether it's a function type or not. So this kind is just the this is the, if you remember the like in the declaration, we just put the tree structure for the type that was given to us by our parser. This is what that struct looks like. So this is the definition of all possible types in our language. So they can either be a primitive type, a pointer type, array type, or function type. And so if you want to check which kind of type it is, whether it's one of those four kinds, there is a kind field on the type that allows you to distinguish between which one of those four types you have. Has anyone ever seen this tagged union type before? Who's seen this kind of C code before? Okay, not many. So this is probably a little unusual to look at, and let me go over what it means. But it's effectively doing kind of poor man's object orientation in C. So this class is still in C. That's the language I can assume you all have. Maybe in the future, if you have any advice on other languages you think future students would like, but because this is in C, but we want to have something like object orientation, we want to have subtyping. You know, a tree node for a type or a statement could be any of several options. And so this is the poor man's object orientation that is a kind of common idiom in C. And here's how it works. So we have an outer structure here, which is going to hold any of the four kinds of types that we have. Who's seen unions in C? Who's seen unions before? Okay, a few more people. Who's seen structs? Hope everyone. Okay, so structs and unions are very similar. The one difference is that in a struct, all fields are always available on every instance of that struct. In a union, only one of those is available at runtime. And it's kind of, I think who's seen object orientation or Java? Did you guys learn this yet? Okay, so most people. So if you have a subtype, that subtype can be used wherever the supertype is used, right? Like you've got, can't think of an example, but car and automobile and car is probably the example that's always used. So you can think of this outer struct as being like automobile, and these unions are saying all the different types of automobiles you have: car, truck, boat, if that's an automobile. And so when we create your AST creation functions, what they do is, depending on which creation function you gave, it'll set, so say you're creating a pointer type. The pointer type AST creation function will set kind to be E pointer type, the enum for pointer type, and then it will set the field, it'll use the pointer type field of this anonymous union here. So that'll look something like, I can actually show the AST creation functions here. So this is code that's actually using that anonymous union. So here kind is being set, and here pointer type is being set. In contrast, if it were an array type, we would set the kind to be array type and then fill out the array type fields instead. So you don't have to worry too much about how this works. You can look up tagged unions or anonymous unions online if you're really interested in like sort of deep, nuts and bolts C programming. But I think of it as effectively as a kind of poor man's object orientation in C. From the usage point of view, all that means is that if you want to know which kind of type you're dealing with at runtime, you check this kind field. And as long as the structure is being used correctly, that kind field will guarantee that the, say it's array, that'll guarantee that the array type field will have the valid data, have the data associated with it. Questions on that? I know that, yeah.
Is an option type a subcase of this?
Option type. I don't know what option. Oh, you mean like some or none, like in functional languages? I think you can implement it the same way. Yeah, I think you can implement it. Has anyone ever seen that in C, option types? I don't know if I've ever seen that, but you could implement it the same way. You could kind of use this as a way to wrap your data and avoid like null pointer errors, for instance, and have some runtime checking or something to avoid that. I think probably the difference here in some types in functional languages, those are statically checked. Here, there's no static checking. It's up to you as the programmer to ensure that kind actually matches the data you've added. So you don't get any help from the compiler here, which is why it's very much poor man's object orientation. But in real object-oriented languages or functional language that do have these kinds of algebraic data types, as they're called, the checking will be done by the compiler. Anyway, this is a little bit of a rabbit hole. From a usage point of view, you can just use it according to the examples that I've given you. Okay, so that's the context here, and so if you ever need to just check whether it's one of those four types in the rules, then this is how you do it. And then finally, the kind of critical part, and this is where probably a lot of bugs may come from, is the type checker, or at least the design I've given you, is to store the resulting types on the tree, annotating the tree with the resulting types. And this is how you do it. So each expression has a type field that you'll set. So whenever you're type checking an expression, you don't return the value. Instead, you annotate the tree with that value. And so there's several ways to implement this. You could certainly implement this by returning it and using type checking that way. I've annotated the tree because when we go to do code generation, it's useful to have access to those types in order to know precision of your types. And so if it's on the tree already, we don't have to do any more lookups. We just annotate the tree. This is really also another design decision, but it's kind of what industrial compilers do. They don't return the type, they annotate the tree and have this augmented tree that has all the types annotated at the right at the symbols for the usage of the code generator. Yeah. Oh, here? Oh, sorry. Yeah, this is just like debugging output. This is just for educational purposes. So when I run it, you can see, and for yourself too, you could do this so you can just see reachability. But yeah, there's no purpose for this here. I use standard error because our type checker will emit the annotated AST to standard out, and yeah, it'll mess up the grader scripts if you have other stuff in standard out. So that's the only use of this here. Excuse me. Other questions on this? So make sure you start early. I think this is due in a week. So start early. And just like with the parser, and it's probably easier to do here, don't fall into the pitfall of code, and then test afterwards. These are very complicated algorithms to debug. And so even if you come to office hours and say like, hey, can you help me fix this? It's going to be hard for me too. It'll take me a while. I'll just do the same thing that I'm instructing you to do now, which is put print statements to figure out where you are in the program, make a test case that is small but will still exercise the bug, and then step through the program line at a time, comparing against the type specification to see if it's doing the right thing. Now, if you're unsure about what the type specification is supposed to be doing, by all means ask. Ask on Ed's discussions, ask in lab. or move on to a different, easier construct. Do your best to understand it, because I know this is a little tricky because this is an informal specification, so there still may be some fuzziness there. So make your best guess. Ask me, ask on at discussions, but make sure you're implementing one of these at a time. Don't fall into the pitfall of program all these functions and then test afterwards. It's going to be very unfun for everyone. Yeah.
I know that end discussion you goes through with asking questions, but does that mean it's okay to put like a screenshot of your code on there?
I guess use your best judgment. I mean, it's not that big a deal if you have a little code. You can also send me a message privately if you're worried. So EdDiscussions does allow you to send just to staff. So if you're worried about violating academic integrity, just post to me only. And if it seems generally applicable, I think I have a way to make it public, I think. Or I can, put an announcement or something, or a clarification. But yeah, you use your best judgment. So you can always send to private. That's probably the safest if you're showing code. But good question. All right, other questions on type checking? So I think if you understand the general algorithm, like we did in the homework, and you then it should give you context when you're implementing this. So I know when you're implementing the nitty-gritty pieces of this, and you're trying to think, what code goes here, you can kind of pop back up and think, well, the whole goal of this is to annotate the tree with the actual type, and to compare those types to make sure there's no type error. And so, if you miss some stuff in the type checking, it's not a big deal. We're not checking comprehensively all possible undefined behaviors. And make sure you're designing test cases that will exercise one function at a time. I've tried to give you enough code to where you can, I've given you main, so you don't have to type check main, and you should just be able to start type checking. And I've given you ident expression, and so you should be able to start type checking assignment and do expressions, and make sure you're testing as you write, instead of once you've written code, don't move on until you've tested it and you're confident at least that it works in some cases before moving on. All right, questions about the type checker? So this is a tricky one. This is a subtle one. The type checker, because it's very meta, because we're effectively taking the program as a whole, and we're doing one of the first steps in processing or trying to analyze this whole program for all of its possible inputs. And so, when you've got an expression statement, you're not trying to evaluate it, you're just trying to infer the types, which is all possible values at runtime, and run this inference algorithm in order to figure out what the resulting types are from these operations. So it is a little kind of mind-bendy. Some other tips, and I had some people asked on EdSTEM discussions as well about this. To make this a little easier, keep references open when you're programming. So have these function definitions available to you. Have the examples here. The template also has examples. Keep the AST reference open. So this is ast.h. Keep this open so that you know how to access the ast.h, so you know how to access all of the pieces of the tree. So each of this is just this struct tells you how to access all the child nodes in this complicated parse tree. So if you're in a call expression, this is the struct for the call expression. So if you need to access the name of the function for the call, you do expression arrow, call expression arrow ident for its arguments. This is the name of it. So keep that reference open. Also keep the reference for the types open, which is it's also in this document here. So this is the reference for types. So if you need to check if something's a function type or an identifier type, you need to get the pointer types, the type that it's pointing to, or you need the function types, parameter types. This is the schema for getting it. And then the actual type rules in this document. So it's kind of a big puzzle-solving exercise. You have this informal description of the type checker, you have your template, and you have to kind of pick the right pieces of the implementation in order to achieve type checking. So strictly speaking, you don't have to use my template. You could write the type checker from scratch. It's a trade-off because you have to deal with whatever design I boxed you into with these functions, but also I've given you code, so hopefully it'll be less work to do that. But it's up to you if you'd like to design your own symbol tables and stuff like that. You can also do that. All right, questions on the type checker? And remember, you can always continue working on it past the due date. Very, very small late penalty to encourage you to just get this working. So, if you're working step by step and actually getting functions written, resist the temptation to just try to do an overnight coding session, just writing everything and then testing later. I predict that it will take you longer to do that. It'll feel slower to go one function at a time, but it'll accelerate as you are able to do each function correctly, and then by the end of it, you'll be more likely to have a working whole system. Okay, so let's get started on the back-end code generation. And today, I'd like to talk to you about how globals and functions are implemented in the compiler, how we translate functions which do not actually exist in the kind of literal sense in the processor and the machine, at least in Intel x86 architecture, and how the compiler implements them in assembly when it does its translation of functions. Okay, so just as a reminder, to always keep in mind is that we're not executing the program that we're reading in. We're not trying to take in the program and figure out what value it's going to have when we run the program. We're trying to take every possible execution of that program. We're trying to take the whole program and rewrite it in a different language in such a way that every input will have the same output in that new language. And here in our compiler, we're taking simple C, and we're trying to write an assembly program that will work the same way, that will behave the same way in terms of its inputs and outputs. And so our kind of general idea here is to take each language construct and produce a template, create a template that if we fill in the pieces of that template will be equivalent at runtime when we actually execute these two programs. And so there are these kind of assembly coding patterns that our programming language captures, which is sort of one of the reasons why programming languages came about, is we have these patterns of behavior that machine programmers noticed, like iteration or function calls, and then the programming language captures these and automatically generates them. So we're trying to translate this, not actually execute the program, and that's got to become you've got to keep that in mind when thinking about how functions are implemented, because it's a little tricky how the actual function implementation works. Okay, so first let's take a look at assembly files. So who's looked at assembly before? Who's seen assembly? What assembly language or what architecture was it? MIPS. This is from CDA, right? Okay, so we're going to learn x86 64 ISA today, which is a lot less friendly than MIPS. Not a RISC instruction set, but it is very realistic, at least for now. x86 is still being used. I wanted you guys to get the feeling of translating to a machine that you can actually run on, your own machine or the virtual machine. Okay, so let me start with an example here. Actually, let me just get a C program. So here's just sort of a random C program. It's got a main method, it does some computation, some printing. It calls this, we have this function f defined here. Actually, it's not being called, is it? Oh yeah, here, it's being called. And we have this function f. got a global variable, we've got local variables. So all the kind of representative of all the kind of things you'll see in a C program. And to compile this, you can do this yourself as well. So you can actually compile this to assembly language using the capital S flag to GCC. So if I take this program abi.c and compile it to assembly instead of to binary machine code, it'll give you a .s file, and it shows you the actual assembly code that gets generated by the C compiler. So this, if the C compiler is right, then this should be an equivalent program. It should have the same outputs, given the same inputs. So let me go over some of the aspects of this assembly file. So here it is with a little better syntax highlighting. Okay. So assembly files have several sections to them. We have data sections, and we have the text section. The text section is actually the executable part. So this is like that von Neumann architecture that you probably learned about, where code is data, and everything's in the same memory layout. This assembly file is kind of reflecting that architecture. So here there are, our global variable was stored in this data section, and so there's some, what are they called, pseudo-ops, I think, in assembly that will allow you to declare space for these global variables. So in C, global variables are just in a fixed memory location, and the assembler will allocate a fixed amount of space for those global variables. If we had strings here, those strings would also be allocated up here at the top, global strings, and local strings as well, string constants. There's several different variations of this. So there are data sections which don't bother zeroing out data. There's a BSS section, which the machine will zero out the data for you. There's a read-only data section for like string constants. And all this is specified in the executable formats. And if you're like really interested in this low-level stuff, you can take a look at this link here on the ELF file format. So the ELF binary is the kind of Linux, Unix standard for binaries. And so inside of your binary file, there's a series of sections which contain the data that's associated with like global values and other things, like I think other systems have like icons and stuff in there, other resources. But it also has this text section. The text section is where the actual code is stored. And so this is on disk. This is what your compiled binary looks like. And then when it's executed in memory, the machine will bring in the compile or the binary version of that text section into memory and then start executing it. So anyway, there's not much to sort of remember here, but you can just define these sections in the assembly file, and the system, there's system-dependent ways on how those get stored in the executable file and loaded into memory. Okay, so the part we're most concerned with is the actual assembly instructions to make an equivalent program to our C program. So now I showed you these. I showed you where you can actually have global variables being defined in this assembly file. But if you look in our C file, there's also a bunch of other variables like int x, argc, int y, q. There's all these other symbols in our program, namely symbols that are used inside of functions, that we don't see anywhere explicitly in this assembly file. So you won't see x anywhere or q. We see this global variable, the name of it. We see f, we see the function. But we don't see any of these local variables. So how is this being stored in our program if our assembly file doesn't even have symbols to refer to these things? Did they talk about this in CDA? So where is this stuff stored? Yeah.
I assume there's some area of data and it just uses offsets of some sort.
So yeah, the answer was there's some place in memory that these values are being stored, and that's exactly right. And then yeah, as we implement it, we'll see how we actually be able to access those memories, that memory. But these local variables, these are runtime allocated variables. They're not statically allocated, at least in our language, they're not statically allocated. So if we look inside the binary compiled file, this ELF file, there's no place in here that allocates memory for all of those local variables. Instead, what happens is when this program gets loaded at runtime by the operating system, this text section, the place that has all the binary for the code, gets loaded into memory, and then the operating system allocates space in memory to hold these runtime allocated variables. So I think in CDA you probably talked about this. What were these sections called? What's that? Registers? Well, registers, where are registers stored? And the processor. Registers are processor local memory. But what about in RAM? What does the system, did they not teach us in CDA? Yeah. Yeah, the stack and the heap. So malloc variables are stored on the heap. And stack, did they teach us in CDA? Did you learn about the heap and the stack in CDA? Who learned about it in the CDA? Not many? Okay, interesting. Maybe this is in systems. Maybe they teach about it. They probably should have thought about heap and stack, but it's how memory is managed at runtime by the machine. So by the operating system. The operating system loads the text in memory and then allocates additional space for you, effectively in RAM. Although, did you learn about virtual memory? Did they talk about virtual memory in CDA? Okay, so this is system stuff. So let me give you a little primer on it then. So yeah, the text section, the actual binary instructions loaded in memory, and then the system also provides a certain amount of space for runtime variables. So when you call malloc will allocate space for you. That's what it does at runtime, whatever space you need. So if you input a number and then call malloc based on that input number, your program will not necessarily crash. The malloc will allocate dynamically space for you as you need it while you run the program. And the way the operating system supports this is as soon as the program is loaded into memory, it allocates, at least virtually, allocates a bunch of space for you. And it allocates two main sections. It allocates the heap and the stack. And the stack is called a stack because actually we will push and pop from it, and this is how cleverly we're going to implement functions. Okay, so heap and stack, kind of the basics of what the operating system gives the running program. Questions on this distinction between the executable and the running program so far? Questions on this? Okay, let's see. Okay, so before we get into it, let's go over kind of at a high level how functions work, and then in the second half we'll actually look at the details of implementing it. So let's start high level. What are functions in a programming language? What do they give you? What are they? Yeah.
Functions take an input, process it, however you decide, and then give you an output.
Okay, that's a good definition. So they define an input and output behavior. So they do some computational input, they give you an output. Yeah.
It's an abstraction of a section of code, and it lets you compartmentalize the program better.
Okay. Yeah, that's also good. So another way to say it is that it's compartmentalizing a section of code, and it abstracts it away. What does that mean, abstract away? How is it abstracting it away?
It hides the complexity. You basically just see what goes in and what comes out.
You see what goes in, what comes out, and how do you refer to that abstract section of code?
The name.
A name, yeah. It abstracts it away literally with just like a new name. You just define your own name, and then it has an input and output specification. Okay, yeah.
Isn't it recyclable code?
Recyclable code?
Like
Reusable, yeah, for sure, yeah, exactly. That's one of the benefits of having a function is that the use of it is reusability. So if you know you have to say compute the square root all over the place, instead of just writing that code every time, you use abstractions, and that abstraction has an input and output specification. For square root, it would be, I give it a number, and the output is a square root. And now I have a new word in my language. I've defined a new word in my language, and I can use that anywhere I'm programming. I can take that word and just say square root instead of actually writing the code to do it. All right, good. Yeah, at least so it sounds like you have a pretty good understanding of function abstraction. That's what it does for you. So this is like my definition. It encapsulates some computation, and it's defined by a name. Usually there are anonymous functions. And it's input and output. And this is exactly what the type checker actually partially checks for us. It checks at least that the types of the inputs and outputs will be what they are expected to be at runtime. And and as your colleague pointed out, there are lots of benefits to having functions. Reuse, you can use it to organize or architect your program. So we have separate lexer, parser, type checker, code generators, and we separate the phases of our compiler into functions. Whatever architecture design you have, functions can help you do that. And as I kind of harp on you a lot about, when testing, if you've designed your architecture and compartmentalized code into separate functions, you can test those in isolation more easily with a function than you can if you just had straight line code. And it helps encourage this kind of careful design of systems. There are more fancy kinds of notions of functions in other languages. So who's ever heard of lambdas? Anonymous functions? It's the same kind of thing? Okay, so lambdas, what are lambdas? Someone who answered. Yeah.
A small function that you just create and use without giving a name.
Yeah, they're anonymous functions. They're anonymous functions. And one of their features is not just, so in the kind of theoretical lambda calculus, lambdas are also values, and you can pass functions to other functions. So you have these higher order functions where functions take other functions' input. And yeah, anyway, take a programming language class and learn more about these higher order functions. Lambdas allow you to create anonymous functions on demand. Functions are data, code is data, so you can pass them around. And yeah, so functions are kind of like the like core abstraction in programming, I would argue, that pretty much every language has and has sort of never-ending uses in programming. Okay, so let's see. Let's take a break here. And before we get into how these functions actually work and how to implement them. And so let's take a break for about 10 minutes, come back at 10:50. Found a bug, which was great. I love when students can find bugs. So basically, my type checker was not checking the type of the array index. And so if you are someone who had a problem with these three test cases, let me show what they are. Array, battleship, and quicksort, which check the array index, you may have noticed that your type checker, if correctly implemented, had additional types on the tree from the given so-called ground truth, which was not ground truth because my type checker just forgot to check the index expression. So you can ignore these for now. We're not going to grade on these, but I'll provide updated ASTs for these so you can see the real ones. But I won't grade on them. And if you have any issue, come to office hours with grading. Correct your grade and everything. But yeah, just be aware that it is right to check the array index type. If you haven't encountered this, don't worry. Just ignore these tests for now until I provide an updated one. We won't test on them. But yeah, thank you. Congratulations on finding the bug. I have stickers to give you, or some other like shirts or something in my office that I'll bring in if you find bugs in my implementation or in the template code. So thanks. Any questions on that? Anyone else have issues with that? With those test cases? That's too bad because these are good programs. These are like real programs that do things like quicksort. All right, first bug of the semester. I'm sure there's many more in there. Okay, so let's get back into how functions actually work. So before the break, we together came up with a pretty good definition of what functions are. They're an abstraction. They're an abstraction that names some computation, which encapsulates some computation you can reuse. And they have some input-output specification. So you can define what inputs it should take, and you can use that output in your program. So and I'm sure everyone has learned programming, has used functions many times. So let's take a look now at how functions work. So let's do this in a text file. Okay, so let's take a function like factorial. Here's a common recursive implementation of factorial. And let me actually put this. So here's a classic implementation of factorial. Questions on this implementation? Probably something I think everyone's probably seen. Okay. So let me make a slight variation of this version of factorial here. Let's do it. Actually, let's just go over this first. All right, if I execute factorial 10, how does this program work? So x is 10. I check this base case here. Is x less than or equal to 1? No, it's not. So we go to the else branch, and this then computes what? X is 10, so it computes 10 times x minus 1, which is 9. Okay, so what happens here when I call factorial again? Where does the flow of control go when I execute that? Yeah. Yeah, back to the start of this function, and importantly, a new version of this function, some kind of new version of this function. What makes this a new version of the function?
I have the image in my head, but I don't know how to describe it. It kind of opens a new slot and stuff.
Yeah, so yeah, that's actually how it's implemented. We actually use the set. Yeah. Yeah, and so now, we have a new version of it where x is 9 instead of 10. So if we just implemented this in a loop, let's see if I can break this in being implemented in a loop. So let me make another version of this function. So I've updated this to assign a new variable y and use that so that I can say update x here. So this version of the code, I just used some temporary, some new variables in order to compute this result of factorial xy. So x is now x minus 1. And the old x is stored in y. So if I had turned this into, say, a loop, so if this were merely just, whenever I see factorial, if I merely just jump here and start executing, and say, turn this into a loop where let's say I turn this into a loop and just reassigned x. by calling factorial. What would go wrong here if I just had a branch, if I just did a while loop here? Let's look at factorial of 2. So if I had factorial of 2, well, let me just show the actual code. So another way to implement factorial is just in a loop. And what I could have done is said factorial passed in x. And then here, instead of factorial, I could have branched, made like a jump statement here. All right, this is going to get complicated actually, like right out. I don't know how to actually write this out. But if we look in our program here, if all this did was to jump back to the top of the loop, then factorial would set y to be 2, x to be 1, and then when it goes to compute factorial of 1, when it goes to compute it, when I go to compute factorial 1, it'll assign, oh wait, sorry, I should probably make this 3 so it doesn't hit the base case. So if I call factorial 2, y would be 3, x would be 2. I call factorial 2. And when I go to enter factorial 2, it'll assign y to 2, right? And it'll assign x to 1. It'll call factorial of 1. And then this will finally return 1. So factorial of 1 will return 1. But if I return 1 here, for factorial calling, if I'm back in computing factorial of 2, I still need to do this computation where I multiply the result of factorial 2 with y. And so I do this computation where I multiply factorial of 1 times y. But y at this point is 2, which is fine. But then when I use that to figure out what factorial of 2 is, so this is the result of factorial of 2. This is going to give me 2. But when I go to finish the computation for factorial of 3, my y has been updated to 2. And it's no longer 3 anymore. So I'll be computing times y again, which is 2. Does this make sense? So this is a little harder to do in text than it is. I probably should have used a diagram to do this. But does this make questions on this? Why, if I don't save a new version of x, a new version of these local variables, that y will get updated by the callee? Sort of makes sense? Let me do a diagrammatic version. I think this will probably be easier to see. So when I call factorial of 3, I end up assigning y to 3 and x to 2. And then I have to compute factorial of x, which right now is 2, and then multiply it by whatever y is. So I have to stop my computation and compute this factorial of 2. And when I do that, I'm going to end up reassigning y to be 2, and then assigning x to be 1. And then when I call factorial again recursively on 1, I still have to multiply it by y. And then I've hit my base case, and so I can substitute this value with 1, according to my base case, and then finish out my computation here, multiplying factorial of 1 times y. But at this point, what is y? Y is 2. So I can conclude that this whole computation here has the value of 2. But what happens, and then I know that this has the value of 2 when I finish out my computation. But what happens when I go to do this computation? When I take the result of factorial of 2 and use it to multiply it by y. What is the value of y? Or what do you think the value of y is? So if I had saved the value of 3, it would be 3. If I just had iteration without using a function, I would have overwritten y to be 2, and this y would have become 2. So I think you all know this because you all use functions. But the kind of key distinction here with functions, beyond just control flow, is that it's also saving a snapshot of all the variables that you're using in that version of factorial. And so if you've ever been confused by recursion, one way to help understand what recursion is doing is if you know how it's implemented in the machine. I think it's a lot easier to wrap your head around recursion, because I think this is something that for a lot of students trying to understand how this recursion works or why it works is pretty confusing. It's probably one of the more confusing aspects when you learn programming. But one way to think about this is that each time I call, well, okay, let me rewrite this in text in a way that might be helpful to understand. So instead of thinking about this as one function, you could think about this as having a different function for each possible input. So instead of factorial of x, I have factorial of 3. And factorial of 3 is a function that calls factorial of 2 and multiplies it by 3. Factorial of 2 is a function that computes factorial of 1 and then multiplies it by 2. And factorial of 1 is a function that just returns 1. Does this make sense as another version of factorial that we could write? So we could end up, write a factorial for every number, write a new function for every version of factorial for every possible input. So you could, I think this is called like currying in like the functional world, where you make create a new function that for that specific input to the function. And so you can think of recursion and the implementation of functions as just kind of dynamically creating each of these instances of the function based on the input parameter. And actually in the machine, when we go to execute this recursive function, this is effectively what happens. The machine will create, or actually our compiler will create code that will cause the machine to create a new instance of this function every time it's called with a parameter. So when we go to actually implement this and we actually run this, in memory what you'll see is effectively this, 3 different copies of factorial. So when we call factorial of 3 on this recursive function, think of it as 3 different copies of that function. And a new function copy is created every time we call factorial. So whatever this value happens to be at runtime of x, think of a new instance of that function being created. Questions on this? Does this kind of make sense? Was recursion presented to you like this before? Who's was presented recursion like this? Okay, one person. Who's confused by recursion? Or who wants to admit it? Okay. Recursion is confusing. So, but okay. So this is a way to frame how recursion works, is that it's just creating a new copy. You could even think of this literally as an entirely new copy of the entire function, where x has been replaced with 3 everywhere. Oops. X has been replaced, and all the values have been replaced everywhere in the function. Okay, so let's see how we actually use this notion of creating new instances of the function at runtime to actually implement this functional behavior. And so the way it works is that function calls, whenever a call is made, in the machine, we're going to basically we're going to keep that copy of all that function variables in memory, and we're going to make a new copy of the function's memory in our RAM. We're going to make an entirely fresh copy of that function. And so the trick is, how can we implement this just using assembly instructions? And the trick is that we're going to use this stack in order to push our copy of the function every time we need to go out and call another function. So if we see a function call inside of one function, if our caller has another call to a function, we keep its copy on the stack, and we make a new copy of another function onto the stack and start executing that function. So that way, when we're done our callee and we're finished computing all that function needs to compute, we can unfreeze and restore the state of that old function so the machine can continue running on the old function that we had. Okay, so let me illustrate what this looks like in the machine. So let's say I'm going to do this with just kind of pseudocode. Let's say we have two functions, function A, or f, which returns g of a plus 1, and the function g returns b times 2. So what happens when we call f of 2? So in memory, a section of memory is allocated for f. This is called a stack frame, or activation record. It's a piece of memory that's dedicated to storing all of the values that are needed to compute f, all of the local variables that are used in f. And so there's space for A, so we go to call f here. So this is f. There is space allocated for the variable A, and given the number 2. And that's all the state we actually need at this point for f. So it's given space to store the value of A. So now when we call G, we create a new space for G. And when we call G here, what is the value of A at runtime when we call, or what is the value of the parameter to G when we call G here? It's 2, right? So when we make this call, we substitute whatever value we have in the expression here to the parameter for G. So we create a new space for B to hold its value. And now we can go execute this body of G and compute that its return value. So if we store the return value on the stack, we can compute B, which is 2, times 2 is 4. We could also store it onto the stack, depending on your calling conventions. And so now that we're done, we can take this return value and substitute it for G in our caller. So we remove this from the stack, so this is no longer needed on the stack. And we can replace the call to G with its value of 4. And then just continue executing this program as if nothing had happened. We still have our value of A. If we were to, say, use A here as well, we'd still have access to the value of it. And we'd be able to compute the return value for F. Questions on this? This kind of high-level description of how function calls work in memory? Yeah.
Would you put in the stack there, would you put the community arrays equal to 4?
So actually, in your machine, effectively, yes, there will be a temporary variable that's created. So when you actually go to implement this, you'll allocate space to hold. Yeah, you could think of it that way, where there is a space in memory that stores the value of that result. Yeah, you can think of it like that, for sure. Yeah, we will actually use the stack. We will use the stack to do that at runtime. So yeah, good insight. Yeah.
Is the call stack different from the stack that holds static or are they the same thing?
So in the machine, they just give you one stack. The operating system gives you one stack, and it's really up to the program to decide how to use it. Yeah, the OS just gives you one stack, and so our compiler will generate assembly code that will create these function stack. They call them stack frames. So it's to the operating system, it's the same stack. To the compiler, we're using the stack for our stack frames. I don't know if that kind of makes sense.
Okay, so but for dynamic memory allocation, would
Yeah.
that be associated with the function stack or with that?
Yeah, with the function stack. Typically, yeah. Yeah, so at least when we go to implement this, we're going to implement all of the function local variables on the stack. We're going to use the stack for it. So that isn't the only way to implement functions. You could also use the heap. If you knew that you had enough space, you could allocate static space as well. You could do it. So it is an implementation design decision. But like in C-like languages, the stack is where local variables are stored automatically. But there are other designs. I don't want to say this is the only way to do it. But yeah, in ours and in like GCC's C implementation, they'll use the stack. Actually, there's like a standard, a convention for using the stack for local variables and parameter passing. But yeah, good question. But you could actually put those values anywhere you wanted and then manage it yourself. So functional languages will actually often use the heap instead because for reasons. If you take a functional language, you'll see you can save these function activations beyond the lifetime of the stack. But yeah, so for our class, for our purposes, we're going to store everything on the stack, but they could be stored in other places in memory if you had a scheme for doing that. Okay, so this is the basic idea where we freeze the memory for a caller function like f, keep all its values on the stack, and then create a new space in memory for our callee, for our new function that we call. And once that function is done, we can resume exactly where we left off in our caller function. So there's another little piece on the stack that ensures that we not only have the memory available to us, but that we also know where to go back to return to resume computing our caller. So this is the return address. So there's another piece of data here on the stack called the return address that whenever we let me give myself some space here. So one of the main things that also gets added onto the stack is the return address. And so I'll just put F here to be the return address. It'll be some offset in F. So somewhere, some actual like memory location of the code that is computing this part of the function will also store on the stack that memory address. So that when we're at the end of our function G, and we've computed the return value, that once we go to restore the state, we also know exactly where in the computation we were running in our caller function. So in CDA, when you learned about the architecture, how does the processor know which instruction to run next? Yeah. To some degree. So in general, how does the processor keep the state of what instruction they're running? Yeah. program counter or instruction register. So I think all these architectures, at least for these stored, the sort of stored program machines, there's a separate register that actually holds the current address or the next address that's going to be executed. And just like all of the registers and all the other state inside the processor, all that is stored in registers. And so the way we actually implement this at the assembly level, so just skipping ahead a little bit, the way we actually implement this at the assembly level is we just take that instruction pointer and push that onto the stack along with all of our data. So in some sense, you can think of this as taking a snapshot of the entire state of your processor, including your instructions, your registers, taking a snapshot of the memory and leaving that on the RAM, and pushing all the information we need from the processor in order to restore the computation that was running when we interrupted it with our function call. So that's the return address. So with these three pieces, the parameters, the return address, the return values, we have all the information we need in order to execute our current function and also return to our prior function. Okay, questions on this notion of freezing state for functions? Okay, let's take a look at what this looks like if we do this for factorial. So factorial is where this freezing of the state actually matters because we'll get the output we don't expect if we're not saving the state properly. So let's take our program we had in pseudocode. So our program was written like this. Okay. So let's compute factorial of 3. Okay, so let's create a stack frame to store everything we need for factorial of 3. So it'll hold on to the current value of x, and it'll hold on to the current value of y. So I'll just do this kind of conceptually where we just store the local state here. Okay, so we have factorial of 3. It's not less than 1, so we go here and we save this local value of y on our stack. And so y becomes 3. And then we mutate x, and so x gets updated to x gets updated to 2. And then we call factorial of x. So right now x is 2. So we create a new slot in memory to store this new instance of factorial of 2. So this was the state for factorial of 3. And this is the state for factorial of 2. In factorial of 2, we have what's the value of x that factorial of 2 has? 2. So it stores factorial of 2 here. Then y gets assigned to x, so it has its own copy of y. And then we update the value of x, just like we did in the first call. And so now x equals 1. We again interrupt our execution in order to execute a new version of factorial. This is calling factorial of 1. And it has its own local state. And its own local state, x is 1. And now we compute the return value here, which is 1. And so its return value will be 1. So when we return to, so we've finished executing this version of factorial of 1. We figured out that its return value is the number 1. And so we restore execution in this version of factorial. And we start right where we left off, which was computing factorial of 2. So we can think of this as saving the result of computing factorial of 2. And now, because we finished executing factorial of 2, we can conclude that this is 1. And since this is 1, what's y here? So, this should be 2. So y is 2. Factorial of 2 is 1, y is 2. So we can conclude that the return value of this instance of factorial is 2. And now we've finished computing this version of factorial. We found its return value is 2. And so we can return to factorial of 3. And here we were trying to compute factorial of 2 in order to compute factorial of 3. And so now we've got its return value, so we know the return value is 2. We know that y is 3 in this version of factorial. We know that factorial of 2 is 2 in this version. So we can conclude that the return value here is 6. Yeah?
I think in factorial 2, you were supposed to write factorial 1, because 1 is factorial 2.
Oh, thank you. You're right. So this should be factorial of 1. Right?
Yeah.
Thank you. Questions? Yeah.
And these stacks, so do you include the, like in factorial 1, do you include like, the return address of factorial 2?
In these stacks?
Yeah.
Yeah. So we go to implementation. I'll show you how the actual implementation looks. So what ends up happening is when we call factorial, we will store the address, the return address, the address that basically the instruction pointer, the memory address of the next instruction that we should execute once we return to the function. And I'll show you how that looks in like the Intel architecture. The memory address actually gets pushed onto the stack. And it's actually the source of kind of classic memory based exploits where you can take over control of the program by manipulating that return address. But questions on the kind of high-level view of this notion of freezing function state in order to implement functions and support recursion in the kind of correct way, or the way we expect when we write recursive functions. Does this help at all understand recursion for anyone who had issues with recursion? Yeah.
How would the compiler respond to, like, let's say, in the factorial recursion, how would the compiler respond to a really large number that takes up a good percent of the stack?
Oh, that's a good question. So yeah, you could pass in an extremely large struct or something, or an array, a local array, and it just goes onto the stack. So it just puts it there. So the compiler will do it. The compiler will put it onto the stack. Arrays, I can't remember if it's part of the C standard or a GCC extension, but yeah, you can put large and even variable length stuff, I think, a GCC extension, but it'll just put it onto the stack if you have a large data. I mean, that's one reason actually why you use malloc. One reason to use malloc and use pointers instead is that you can allocate this stuff on the heap, which is usually given more memory by the system than the stack. Or, well, they actually share the same memory. But yeah, typical design is to store big stuff that's sort of persistent on the heap. But yeah, it'll just put it right on the stack. GCC will just put that giant struct for you on the stack, and another reason is that it'll end up copying it to the stack. So if you're creating some value here, and then you want to pass it on the stack to here, well, if you have a naive implementation like we have, it'll end up just copying it here to the stack. Whereas if you had a reference instead of pointer, you could just share that data between the function calls. But it'll just put it right on the stack without any other programming technique. Other questions? So hopefully this gives you a good understanding of recursion, and it just falls out of the behavior of a function where we just freeze all of its state. And yeah, if you're ever confused about what a function does, you can just make this kind of call tree where you illustrate each of the calls as separate functions. You just treat them all as separate functions and try to reason about, for like a finite input, reason about what'll happen. So same with binary trees. If there are two calls to factorial, or like a binary tree, then there will be effectively a tree of states. You can still represent that on a stack, but you can think of it as a tree, a call tree of states. All right, questions on recursion conceptually? Okay, let's see how to actually implement this in assembly, and then eventually see how we can actually make a compiler generate code that will, because remember, we're not implementing the stack frame in our compiler, we're generating code that will create stack frames, which will make this a little bit more confusing, a little bit more mind-bending. Okay, so we need to give enough information so that we can restore this function's execution exactly as if it had never left. So all the information we need the parameters as the input, we need any local variables that are created, we need the return address, which your colleague pointed out, in order to return back to the point of execution in the program before we left. And we also need to know how to return to the stack frame, to the previous function stack frame. So here I kind of hand waved it away. I just said once we're done here, we go back to this state. But the machine needs to know where in memory this state is stored, where this stack state is stored. And as the compiler writer, we can actually statically figure out, or we can actually statically generate code that will ensure that we've saved where this previous caller's stack frame in memory was. And that'll help us be able to support these nested calls. Okay, so for parameter passing, there are several options for actually storing this in the Intel architecture. Their calling convention, or at least the one used in the Unix world, the calling convention is to store data both on registers and on the stack. So you could just push all of your parameters on the stack, but why would you want to use registers to pass parameters to functions? Or not? Yeah.
Because registers, if you want to use them because registers are absolutely fast.
They're much, much faster. So if you remember in CDA, yeah.
Yeah, I was going to say, you also don't want to use them because you don't know very many.
Yeah, good. So those are the exact two trade-offs. If you use memory, loads and stores are much, much slower than register stores and loads. But on the other hand, registers are limited. So if your caller function has a lot of data that it's working with, well, if you have to use those for parameter passing, you have to save them somewhere. You have to save them on the stack. So you do have this tension between using registers and registers and RAM for parameter passing. The Intel x86-64 API, or calling convention, ABI, describes using kind of a combination of both. So for the first 6 parameters, they're given registers. So you've got, I don't remember how many registers you have in x86, maybe like 32 or some. You have a decent amount of registers to work with. And so in the Intel x86-64 calling convention that we're going to use, which will allow you to interoperate with other C functions, hopefully, the first 6 parameters go on the registers, and anything beyond that get pushed onto the stack. And so it's kind of I think it's probably just kind of a balancing exercise. It's a trade-off. But this is the standard. And having it as a standard means that anyone who compiles code, any libraries that compile, these functions will work together because they need to know where to look for the parameters. Yeah.
So what if we have, what if the first 6 parameters are something that's not
Like structs. The ABI handles this. Let me get the reference for this. So I forget offhand exactly how this is done, but there are detailed references that, where is this? I'm pretty sure it's here. Oh no. So there's other registers. Let's see. There are. I can't remember offhand. There is a way to pass in with registers larger values, but I don't remember what it is. It's in this description here somewhere of the ABI, but I can't remember what it is. It may end up just being something you have to pass. I can't remember how it works. I can't remember, but it's in these documents that I've linked. Ask on Ed discussions, and I'll dig up the resource because I cannot remember how it works.
And I remember hearing the CDA at some point that, and I don't know if this is relevant to Intel x86, but if you have a field that's much more frequently used, there's like a process that moves it over to the register. It's a stack initially for optimization purposes.
You mean outside of calling functions, just like in?
Most generally.
For sure, yeah. So there are compiler optimizations that will. Do you mean at runtime, or in the compiler?
I believe this is starting with compiler.
Yeah, the compiler will. So yes, optimizing compilers will try to. They have algorithms for trying to keep variables in registers as long as possible. There are several algorithms for doing this, just to avoid having to write back to memory in the first place. This is unrelated to the ABI, though. I don't think there's a way. I mean, you could write your own function API, ABI, and pass everything in registers if you wanted. It just wouldn't interoperate with other library calls. But yeah, there definitely are optimization techniques that will avoid, for the exact same trade-offs that we just discussed here, avoid putting variable data back into memory and keeping it in registers as much as possible. Yeah, optimizing compilers can do that for sure. But here, I guess if you're writing like library calls and you want to interoperate, you'll need to follow this, unless the other developer also agrees with you. I don't remember. That it's now bugging me how to let. I remember there were other registers you could use. I don't remember what the convention is when you have longer data that doesn't fit in a single register. That's the Windows API. So as you can see, I'm not an expert on assembly programming, so this is not my expertise. I know just enough basically for writing a compiler, like a toy compiler. But okay, but yeah, the resources are in here. If you ask on that discussion, I'll dig up the details. But yeah, there's this kind of cool site, wiki.osdev.org, that gives a whole bunch of low-level information about operating systems, about the actual system software and their actual specifications, including these calling conventions. But yeah, I don't work with this is not my expertise. Okay, so let me get back to where's the ABI? Okay, so in the actual implementation, in the actual Intel ABI, this is what your stack frame looks like. So we have a function here. It takes these 8 parameters, does some computation, has some local variables. And so according to the Intel x86-64 ABI, we put the first 6 parameters in these predefined registers. It's just by convention, and so these handle the first A through F parameters, and then subsequent parameters are pushed onto the stack. So by convention, at least in Intel systems, the heap grows upwards, so as you allocate memory addresses get higher, and the stack starts at the end of your address space and grows downwards, so that you allocate memory going up your memory, and stack, as you call functions and create stack space, grows down. So that way, you kind of maximize the amount of addresses you have for both without running into each other. And so we're going to have to kind of, when we create our assembly instructions that manipulate the stack, we're going to be moving the addresses down. We're going to be moving in the negative direction. So H and G are pushed here onto the stack. And then the next thing that's pushed onto the stack is the return address. So that's basically your instruction pointer, your program counter. That's pushed on the stack right with everything else. And this, so let me talk about this RBP in a second. After this RBP thing is pushed, here are space for the local variables. So the local variables are also allocated space onto the stack. Okay, so this RBP, this is called the base pointer in the Intel world. And the base pointer points to the calling function's stack frame. So this is how we know, like in our toy example here, this is how factorial of 1 knows how to find the previous stack frame for factorial 2. It saves the address in memory of this stack frame. It actually literally saves the address of it. So it saves the code instruction location, the next instruction to execute, and it saves the stack frame. And by knowing both of those things, we're able to restore the execution of that caller function as if it had never known that it ever was frozen. So that's what this RBP is, and this is like the Intel lingo for this. RSP is the stack pointer, so the stack pointer always points to the top of the stack, which is the most negative number because we're going down in addresses. So stack pointer is always pointing to the top of the stack. There's an instruction where you can actually push values onto the stack. And this RBP is a special register that you could use it for anything you want, but according to the calling convention, is meant to always hold a pointer to the current stack frame. And so the current RBP points to this address in memory. And whenever you create a new function call, so let's say the previous RBP is pointing here, the base pointer. When we create a new function call, it'll push the parameters, push the return address of its own function, and then the new function will save a pointer to the old stack frame. It'll save this pointer and update it to be its own stack frame, and then push any variables for its local variables. Questions on this? Does this kind of make sense? This is like the physical implementation of that notion of saving stacks. And now all of this is a convention. Yeah, go ahead.
So every function call has its own RBP?
It has its own RBP value. It has its own address it has its own base pointer address. But RBP is a register.
Yeah.
And so every stack has its own RBP value. But RBP is one register, and so it can only hold one value at a time. And so when this gets unwound, when the function finishes, what happens is all of these local values get popped off the stack because the function's done executing, doesn't need it anymore. And then the next thing it does is it pops this old RBP off the stack and restores the base pointer. So, and that's actually why it's here. That's why it's here in the stack frame. So after we pop all of this off, the next thing that happens is this base pointer gets popped and stored into the RBP register. So this RBP register gets moved back down to the caller's stack frame. And then the caller will pop, actually the machine will, the next thing you do will pop off. You'll pop off the address too. So there actually are helper instructions that will help you do this. You don't have to literally do all of this jumping around and branching. Intel has instructions that will do some of this for you. Okay, so this is just a calling convention. There are lots of ways you can implement functions on the stack, storing stack frames. The calling convention in the Intel world is that this stuff in green, this is all done by the caller. So the caller pushes parameters, pushes them, puts them in the registers in the stack. The caller saves its own return address. And all the stuff in light blue is the callee. So once flow of control is transferred to the callee, to the function, that function is supposed to save the old base pointer, update it to its own base pointer, and then push any local variables. Questions on that? It's just a convention. There's many ways you can implement this. This is the Intel System 5 ABI. What about return value? So there's no notion of a return value here. In the Intel ABI, it's passed back as a register. So it's not stored on the stack. Instead, it's in the actually it doesn't even show it on this page. But the return value is stored in a register. Maybe it's here in this description. So yeah, so the return value is stored in the A register, basically. So, and there's some complexity if it's like 64-bit. But the return value is also passed back in a register, which I think means if you're trying to return a struct or something, yeah, you're not going to be able to do that. It has to fit in a register, from what I understand. Or the compiler. There may be something in convention for returning, just like for parameter passing, to return larger values. Okay, questions on the calling convention? So this is Intel's support for handling these stack frames. So the RBP register is intended to always point to the current function stack frame. And now this is a convention, so if you have a bug in your compiler or a bug in your program, RBP may be the wrong value, but this is its intended use. And it's enforced by us, the compiler writers. We're going to generate code that will ensure that RBP always points to the current stack frame. The RSP register points to the top of the stack, which is the lowest address. There are instructions for pushing and popping data from the stack. So this is what we'll use to say, store the old base pointer. We'll push RBP and then overwrite RBP. And then there are also functions to help you transfer flow of control. So you don't have to actually do a branch and capture the return value. There are two helper functions here. Call. Call does two things. It saves RIP. RIP is the instruction pointer, which is aptly named given the security exploits that have involved the instruction pointer. But the instruction pointer gets saved, pushed onto the stack by call, and then call will then branch to the function's address. So you'll say call, and then the address of the instruction of the function. Call will push onto the stack the instruction pointer, and then branch to there. And return does basically the opposite. It'll pop off whatever was on the top of the stack, which, as long as you've generated the assembly code correctly, will be the instruction pointer. If you've done it incorrectly, it may pop off an address that is not code or not accessible, or exploit code if you've been attacked. It'll pop that off and then branch to it. So the kind of the inverse of call. So questions on this? Okay, so let's take a look at an example of an actual function call, and I'll use my simple C program to illustrate this. Okay, so here's a simple C program that has main. Main calls a single function f. It passes it two parameters, adds them together, and then returns them. Oh, whoops. It's right now. It's doing type checking right now, so let me rebuild it to do compilation. Okay, so here is the output of the simple C compiler. I will save it into a .s file. So here is the emitted assembly code from that function. So recall that Here's, recall, this is our function. We have this function f here, and we have main. Okay, so let's look at the caller first. So we can see the call assembly instruction here, calling the address of f, and so in assembly it'll do labeling for us. And so here is the so it'll become more clear when we actually get into compiling the rest of the code here. But this is saving the parameters in the two special registers that we use for passing parameters. So RSI, RDI. So recall here that RDI is the first parameter, RSI is the second parameter. And for reasons that'll become clear when we actually compile expressions, RDI and RSI are being set here inside of our caller. Okay, so here are two parameters being passed, A and B, and then we call F. So let's see what happens. Let's see how F works in order to implement the rest of our ABI. So recall that we just passed parameters here. So we passed them in the registers, so there's no need to push anything onto the stack in this example. And then where's the return address? How does the return address get stored onto the stack? Or did we didn't actually push it onto the stack, so how did the return address get stored onto the stack? Yeah. Call, yeah. So the behavior of call is to push the return address for us onto the stack. We don't actually have to read the instruction pointer. It'll push the instruction pointer onto the stack for us. And now we're into the part that the callee is responsible for managing on the stack frame. So here is what's called the prologue. The prologue sets up the rest of the stack. So here, it's saving our base pointer onto the stack. So that's push RBP, that's pushing the old base pointer. And now it's setting the base pointer of the new stack frame. And so the kind of clever trick here is that once we push the old base pointer here, the stack pointer is also pointing to this address in the stack. And so the new base pointer is taken by reading the old stack pointer, or by reading the current stack pointer is the new base pointer. So the stack pointer is being updated as we push things onto the stack. After we push the old base pointer, by convention, that's the address of our new base pointer, the address of the stack. And so we just update the base pointer by moving whatever address is in the current stack pointer into the register, the RBP register. Kind of makes sense? So this is just implementing the convention here. And then this subtraction here, this is making space on the stack for local variables. So instead of having to literally push each time for every local variable, at least in this simple C compiler that I designed, we just add up the amount of space we need for local variables and just subtract it from the stack pointer. So this will update the stack, this will move the stack pointer down to make space for local variables. So why is it subtraction and not addition? Why are we subtracting from the stack pointer to make space on the stack? Yeah. Oh, yeah. Yeah, right, because by convention in the Intel world and the Linux world, stacks grow down, and the push instruction actually moves the addresses negative. It subtracts from the address. And so if we want to quickly push onto the stack, quickly make space on the stack, we can just subtract from the stack pointer. All right, questions on the function prologue, how it implements this convention. All right, and then there's the aptly named epilogue. The epilogue does the reverse. Here it's actually setting the return value, but we'll talk about that more when we compile the rest. So whatever return value, if there is a return value, goes in AX. And it does the reverse here. So we sorry, so this is, so I was getting confused by RBX and RBP. So we update the stack pointer to be the okay, sorry, I'm confusing myself here. So we want to take this stack pointer and remove all of the local variables. So the way we do that is we just make the stack pointer to point to the current base pointer. So that undoes the subtraction, moves the stack pointer back down to here, back down to our base pointer. And that's the exact location where the old base pointer was stored onto the stack. So in order to restore that, we pop whatever value is on the stack and store it into RBP. So that will both move the stack pointer back up and take whatever value is in the stack and put it in the RBP register. And because the first thing we did was to push the base pointer is now at the top of the stack, so when we pop that, it restores the old base pointer. And then we call return. And so what does return do in the Intel world? It pops off whatever is on the stack, and because we used call in order to create the stack, it's the return address. It pops off the return address and branches to it. And that's it. That's all you need to do at the assembly level in order to implement the Intel ABI. Questions on this? Okay, so let me compile this program. And, oops. And there's a kind of a nifty set of scripts that work with GDB, and I've given instructions for using this, because this will help you when you actually debug your output code. We can actually watch how the stack frame gets updated and how this calling convention works by looking at so what this output will give you. So I've given you instructions for actually like making your GDB have this nice, pretty display. So these scripts will give you a view of all the register values. It'll give you a snapshot of the code that we're currently on, and it'll also show you the stack. And so there's a lot of extra debugging going on here, like it shows you if things are pointers, it shows you what's at that pointer. But all we really need to look at is our registers, including our instruction pointer here, our assembly code, and our stack. Okay, so we're at the beginning of main here. So you can see here, we're at the beginning of our main method. And main is also a function, just like every other function you write, and it also implements the ABI. So let me step through the main method until we get to our function call. Okay, so here we are setting the two parameters, RDI and RSI. And so in our code, if we go back to look at our code here, the two parameters were numbers 1 and 2. And so what we should see is that RDI and RSI contain the values 1 and 2. So after we set up these parameters, we set RSI and RDI. If we look at our registers here are those values, 1 and 3 in our registers. So we'll talk more about when we get to expression evaluation, how that gets set up, but this is how we create you can see here, this is how it's following the calling convention. Okay, and then here's the call instruction. And so remember, the call instruction will push the return address onto the stack and then transfer flow of control to the address of F. So you can see here, this was pushed onto the top of the stack. And conveniently, it actually tells you what instruction it is. So it's actually, if we were, well, you can't see it anymore because it moved the flow of control to the beginning of F here. But if we were to look inside of our assembly instructions here, you can see that the next instruction after call is this push RAX. So that should be the that should be what's the return address. It's the next instruction after the call. Okay, so now our flow of control is in F, and here we can see it implementing the calling convention. So the first thing it does is it saves the old base pointer onto the stack. So we should see that appear here onto the stack. So here's the old base pointer. So this is the address of the old base pointer. It's just showing you the value of that address. But here's the address of the old base pointer. And so here's RBP here. It's saving that address. That's our old main stack frame. That's the stack frame for main. And then we're updating RBP. So we should see RBP here change to whatever the current stack frame address is, which is actually given here. So let's see if we can see that. So yeah, you can watch RBP change here. RBP is now updated to the current stack pointer. And our old RBP is still here safely on the stack, along with our return address, all safely stored on the stack. And so now we actually implement the contents here, which is gonna, I forgot one step of it. We create space on the stack for our local variables. And so here we'll see the stack here move. So now you can see there's more space here now on the stack. Our return address, our caller's RBP is still safely stored onto the stack, and now we've got some extra space here for local variables. And then we implement what's inside here. So I gave a very simplistic implementation here. So the first thing that happens is we save the parameters to those memory locations. So I've basically created enough space for all of our local variables, including the parameters. And so here we're just taking those parameters out of the registers and putting them onto the stack. An optimizing compiler may know not to have to do this, but I have a very naive implementation that will just take all the parameters and push them on the stack. So we're going to see 1 and 3 now appear onto the stack here. So here's space for our local variables. So looking at our code, our local variables here are A and B. So here is the space for A and B on our stack. And through our calling convention, we've pulled them out of RDI and RSI to put them in our space for local variables on the stack. And then this is the code that's going to just compute the addition. We'll talk about that more in a couple weeks when we talk about how the expressions are compiled, but this is the code that's going to be computing the result A plus B. And so we're going to store that result in RAX. So here's the result here. And we'll go into more how that actually works, but just this is the return value for, and you can see here it's stored in AX per our calling convention. And now this is the epilogue. This is the code that will tear down the stack and return flow of control back to the caller so it can take that return value and continue its computation. Okay, so what does the epilogue do? So what does this instruction do in the epilogue? If you're still following along. So this will take the old, it's this one. It will take the old base pointer and update it. I'm sorry, it'll take the old stack, it'll restore the, I'm getting tired too. So it'll take the old stack pointer and restore the stack pointer by taking the current base pointer and blowing away the stack pointer. So this is where our current stack is pointing at the top here. And so you'll see the whole stack just collapse and get blown away because we're removing everything we pushed onto the stack. So the stack has been blown away. And now, according to our calling convention, what should be on top of the stack is our old RBP and then the return address and then all the old parameters. And so now that the old base pointer is on the stack, the next thing we can do is restore the RBP register. So this will update RBP to be the old caller's base pointer. And then return, we'll pull this, because this address, return address, should be the next thing on the stack. It'll pull that off the stack and branch to main. And so when I go to the next instruction, we should see the instruction pointer update and flow of control return to main. So here we are back in main with our updated instruction pointer. And then for the rest of the cleanup, the caller, because it was responsible, if it had any stack manipulations that it did to push parameters, it would pop those off the stack now. There are none, so instead it's going to continue on its way, computing the rest of its function. Okay, questions? So you have this recorded at least, so you can go back and walk through it. I've given you instructions on actually using the GDB. You won't actually. I'll give the assignment for next. It's several weeks before this is actually due. We'll talk more next week about implementing the back end. Okay, so questions? All right, let's leave it there. Have a good weekend, everyone.